Page 168, astrocytes. We ended last Wednesday by giving or talking about 6 different neuroglial cells. We decided the neuroglial cells were the ones responsible for any kind of cancer that might be in the nervous system, simply because they have the ability of mitosis. So, several of them they talked a little bit about, but the one they're going to talk the most about here is astrocytes. It is the most abundant. So they give us 7 different functions. Number 1, astrocytes take up potassium from extracellular fluid. Well, it stores it. If we need it, we have it available. Too much potassium out there could cause some serious neurological damage. Not enough potassium can cause neurological damage. So danged if you do and danged if you don't. So astrocytes help monitor that. Number 2, astrocytes take up some neurotransmitters released from the axon terminals of neurons. Take up some neurotransmitters. It depends on which one it is. Say it's dopamine or serotonin and we use it and we don't need to use it right now, we take it up to store it and use it again later. Number 3, astrocyte infeet surrounding blood capillaries take up glucose from the blood. So we're bringing glucose into the nervous system. Number 4, astrocytes appear to be needed for the formation of synapses in the CNS to join a presynaptic to a postsynaptic neuron. Apparently, astrocytes are needed for that. Number 5 is a fairly new one. Astrocytes regulate neurogenesis in the adult brain. And we question the fact that we actually have neurogenesis in the adult brain. We talked about the things that have to be in place to grow back a severed neuron or a severed nerve of some kind. So that to me would be a little question, number 5. Number 6, astrocytes induce the formation of the blood-brain barrier. This one's big. This is protection and also a hindrance if we're trying to fix something in there. And number 7 is also a new one. Astrocytes release transmitter chemicals that can stimulate or inhibit neurons. They can stimulate or inhibit neurons. So the list is mighty that we see functions of astrocytes in, highly functional in a variety of different ways. Most of them pretty self-explanatory. They give a little explanation with each one. You can read through those, but for the most part, we've summed it up. They do list the blood-brain barrier at the bottom of 169, and it's a set of capillaries in the brain. Do not have pores between adjacent endothelial cells. The endothelial cells of the brain capillaries are joined together by tight junctions, unlike in other parts of the body, in other organs, and other places. Therefore, it is very specific in filtering things in and out. In fact, they tell you the brain cannot obtain molecules from the blood plasma by non-specific filtering. So it is very protective of the nervous system, brain, spinal cord, spinal fluid, and serves that purpose well, but makes it extremely difficult for us to get things into the brain. They talk about Parkinson's on 169, the bottom of it, and then Parkinson's the problem with Parkinson's is that it is the degeneration of the dopaminergic neurons. That's what's happening. The neurons that receive dopamine in the nervous system are degenerated. They're not functioning. It takes more dopamine to get them to do something now than it used to. Now what causes that, if we knew, we'd probably have a cure. We have a lot of theories, and there may be several things that's causing it. There's even some data out now that football players are coming down with Parkinson's, and they think traumatic head injuries is basically what it's coming down to. So it very well could be. They talk about here that in Parkinson's, these people, to treat this, they want to put more dopamine in the system. And we're less sensitive with the receptors, so we're adding more dopamine. We can't get dopamine through the blood-brain barrier, so we found a synthetic form called levodopa that we can sneak through there, and it does help the process. But this blood-brain barrier is so specific that in treating meningitis, there's only a handful of antibiotics we can get through there to treat meningitis. So serves a great purpose, but becomes a hindrance when we're trying to treat something in there as well. And they'll talk about Parkinson's a little bit more, but I found that interesting with football players and Parkinson's, but it makes sense with traumatic brain injuries. And it doesn't have to be football players. I mean, those guys they get beat up a lot.
Boxers, a lot of boxers have it too.
Yeah, well, Muhammad Ali, it's amazing he's lived this long, but his rope-a-dope theory of boxing took a lot of punches to the head, and how he won some of those battles, I don't know. I'm not sure he ever slung a punch, but they never took him down. But I saw him on TV at a baseball game the other day. They showed him sitting over there. You're right. Page 170, looking at electrical activity and axons. So we're starting a little component here of what we had up on the board last Wednesday. So I'm going to kind of just show you as we go through here. They're talking about resting membrane potential, which is what we had at each node of Reindeer. And what is standard resting membrane potential? Negative 70. The range would be negative 65 to negative 85 millivolts is the range. So that's resting potential, or what's called polarized. Depolarization is an action potential. That's when we have the influx of sodium triggers an action potential. And of course, repolarization recharges that back to a negative 70. Now, we have an influx of sodium in this action potential. The influx of sodium comes in and forces potassium out. They're going to tell us in a couple of pages here, maybe the next page, that sodium has one gate. It tends to be voltage regulated, but it does flicker from time to time for some reason. So this flickering gate may allow a sodium to flood in just in a resting state. That's not near as important as the two gates that potassium has. One is voltage regulated and the other one is not. So this gate, one gate stays open all the time. Potassium may just flow in and out as necessary. So are we going to sit on negative 70 millivolts? That's why we have a range of negative 65 to negative 85, and we're going to stay within that range. Now as soon as an action hits and the sodium rushes in, just before the sodium gate closes behind it, the voltage regulated potassium gate opens and forces it out because positives repel. And then electrical current that was there, of course, re-energizes the original stimulus to the next level. Okay? So we end up conducting without decrement, without loss of amplitude. So they tell you in there, when we repolarize this, when we get it back to a resting state, how many sodiums do we pump back out compared to potassiums we pump in? Do we remember? 3 to 1. 3 to 2. 3 to 2. 3 sodiums out, 2 potassiums in. And that's what they're telling you there on 171. And 172 kind of finishes it off, telling us that a fraction of a second after sodium channels open, they close, do an inactivation process. Just before they do, this causes the gated potassium channels to open. Because the opening of the gated sodium-potassium channels stimulated by depolarization, these ion channels and the axon membrane are said to be voltage regulated. Voltage regulated. The rest of 172 and 173 is basically telling us the same thing. They're giving us kind of a positive feedback loop in the regeneration process or repolarization process. But then they talk about local anesthetics at the top, and we discussed that the other day. Then we go over to 174 and we get into what's called the all or none law. When you hear the term action potential, this is the all or none law. There'll be enough threshold stimulus, whatever level that threshold is at, to trigger a response or not. That's all or none. Muscle contractions are all or none. It's either enough to get a muscle contraction or nothing. We're not just gonna sit there and start stiffening and finally somewhere out here you get a contraction. It doesn't work that way. It's all or none. So the amplitude or the size of the action potential is therefore all or none. The depolarization is below threshold. The voltage regulated gates are closed. We have to reach threshold to throw a gate open. When depolarization reaches threshold, the maximum potential changes. Because the change from -70 to +30 and back to -70 lasts only about 3 milliseconds, the image of an action potential on an oscilloscope screen looks like a spike. That's because it happens fast. Oscilloscope, medical, you've seen some of those, haven't you, since you repair that kind of stuff?
Repair? I don't repair it.
You don't repair those? I thought you was a technician. You just run them. Okay. On 175, refractory periods. Now, I used a reference to this the other day. I said we have a relative refractory period and an absolute refractory period. And this is the time frame in which the question is, can we conduct another impulse? Can we regenerate another impulse? So the interval between successive action potentials will never become so short to allow a new action potential to be produced before the preceding one is finished. Now that's a pretty good general rule. Typically, we're not going to conduct another impulse until the first one's done. But there's a couple of exceptions to the rule here, and it's got to fit a very small niche. If the second stimulus is applied during most of the time that an action potential is being produced, the second stimulus will have no effect on the axon membrane. This membrane is said to be an absolute refractory period. It cannot respond to any subsequent stimulus. So can we, while we're working on the first one, conduct another one? Absolutely not. Absolute refractory period. Absolutely not. How many times you heard that in your life? And then at the bottom it tells us that we're, during the time that the sodium channels are in the process of recovering from their inactivated state and the potassium channels are still open, the membrane is said to be in a relative refractory period. So in a relative refractory period, we're not a +30, but we're headed back to 0. And eventually -70 millivolts. If we're at 0 or slightly negative, and the second impulse is greater than the first, we will attempt a conduction. And that's relatively speaking. That's pretty sad jokes for Monday morning, but hopefully it'll help you remember. Cable properties. Cable property is our ability to conduct an electrical impulse. If we compare ourselves to copper wire, we're pathetic. Bottom line, we do not have a very good ability to conduct electrical impulse. Yet, I think we do pretty well. We talked about thin unmyelinated, thick unmyelinated, thin myelinated, and thick myelinated. And there's your slowest to your fastest in those cable properties. And they list, I'm not sure where they actually list these, but that's what we're headed into, 176 and 177. And our slowest is a thin, unmyelinated, which we said the other day we'd probably find in the digestive system. It's a very slow process. Your fastest could be a reflex found in skeletal muscle, which is thick myelinated. Myelin speeds conduction. This is where they tell you on 177 that it's important that we don't say conduct, but we say regenerate. And then in the next paragraph, they say that an action potential produced at the last region of the axon has the same amplitude as the action potential produced at the first region, so action potentials are thus said to be conducted without decrement. So we've got a little conflict in terminology here, but we know, I think we get the gist of the meaning. It's going to continue at whatever level it started, whether you're going to say regenerated or conducted. Both, it plays really a role in this. So at the top of that one, it's important to recognize that action potentials are not really conducted. Although although it's convenient to use the word. Each action potential is regenerated. Then the next paragraph says they are conducted without decrement. That's the kind of stuff catches me when I'm reading this. The conduction rate is substantially faster if the axon is myelinated. We've already noted that, and I think we should have that one stuck in our head. If it's myelinated, we have less resistance because we're jumping from node of Ranvier to node of Ranvier, and that's saltatory conduction, which they're mentioning here. Jumping from node to node, we just hit the high point, so to speak, where we get regenerated, and if we started making more contact with an axon, we'd slow way down because of resistance, too much resistance. 178, this is where they're going to give you conduction rates in the human nervous system vary from 1 meter per second in thin, unmyelinated fibers to mediate slow visceral responses to faster than 100 meters per second, just a mere 225 miles per hour, in thick myelinated fibers. So in summary, the speed of an action potential conduction, or they should have said speed of action potential regeneration, but they didn't, they said conduction, is increased by diameter of the axon, because this reduces resistance, and number 2, myelination. Larger the axon, myelination, we speed conduction. Then we make it to the synapses, which we had going from a presynaptic to a postsynaptic. We had as a synaptic cleft there we had to deal with. And whether it be from one neuron to the next or from a neuron to a muscle, neuromuscular if you will, we still use the same concept to getting this done. We're electrical down the length of an axon, and we're chemical getting from one neuron to the next, or one neuron to a muscle. And that's what they're telling you there on 178. 179, electrical synapses and gap junctions. Well, gap junctions is what you'd find in cardiac muscle. And in cardiac muscle, it allows smooth flow of electrical current instead of jumping. Not a lot of jumping going on in cardiac muscle because that's going to create a herky-jerky effect in the muscle contraction, which we need very smooth contractions that are very rhythmic and very steady. And so we have a little different makeup inside the cardiac muscle, which they refer to as gap junctions. Chemical synapses. The presynaptic endings called terminal buttons. I think I had synaptic end buttons or something is what I called it up there the other day. They're the ones that hold the neurotransmitter that synapse the gap or bridge the gap as there is a threshold stimulus coming down the length of an axon, so it doesn't miss a lick when it gets there. So it bridges the synaptic cleft. On 181, the clinical application at the top talks about tetanus toxin and botulinum toxin, so that's a nice one to look at. Talk about flaccid paralysis or spastic paralysis. You know, tetanus will give you spastic paralysis. Botulism gives you flaccid paralysis. I'd rather not be paralyzed, either stiff or highly flexible, either way. That'd be awful, wouldn't it? Loose as a goose and can't do anything, or be stiff as a board and can't do anything. And these people are alive like this for a while before it ends up killing them. But can you imagine be helpless like that? Those are both just horrible. At the bottom 181, there's 2 broad categories of gated ion channels, and we've discussed this. I'm just pointing it out here that's in the book. Voltage regulated and chemically regulated. Voltage regulated channels are found primarily in the axons. Chemically regulated channels are found in the postsynaptic membrane. So we're in a synaptic cleft, really. Voltage regulated channels open in response to depolarization. Chemically regulated channels open in response to the binding of postsynaptic receptor proteins to the neurotransmitters. So that neurotransmitter produced that bridges the gap, that's what is triggering this. Leads us into what's called excitatory postsynaptic potentials, EPSPs. In the comparison, the major difference between excitatory postsynaptic potentials and action potentials is this. Action potentials are all or none. It's either threshold level or not. Excitatory postsynaptic potentials are summated. They can start here. If threshold, let's say threshold's here, this is all or none. This would get you an action. EPSPs can start down here and start summating. A little bit of neurotransmitter given off, but not enough for a response. A little more given off, not enough for a response. We continue to give off enough neurotransmitter, but not getting a response. But if we finally give off enough to reach threshold level, then EPSPs turn into action potentials. Okay? And that's the difference. I don't know that the book has a great example of this. Here's my example of this. Little Johnny. We all know about little Johnny, right? Let's say little Johnny's making some kind of annoying noise in his bedroom. Mom, multitasking as she does every day, she's got a load of laundry, something cooking, and the phone, talking to, probably barking orders at the husband. And heads down the hallway past little Johnny's room to put up clothes that she's been folding all morning. As my wife would say, buttloads of clothes. Lots of clothes. Little Johnny's making this irritating noise, and so as she approaches his door, she says, "Hang on a minute. Little Johnny, will you stop that, please?" "Yes, Mother." And she goes on about her business. Comes back by, he's kind of started it again. About the time she takes a step away, he starts it again. Comes back by, "Johnny, I've told you once, this is twice, I'm not telling you again, stop that." We've got a little neurotransmitter, but not tremendous action, do you think? A few minutes later, Mom walks by there and he's really fired up the irritating noise again. This time she says, "I'll call you back." Closes the phone, sets down the laundry, never says a thing to Johnny, but jerks him up and thrashes him a new one. I think she reached action potential. We had excitatory potential here, but it wasn't enough for action. A couple of warnings. But that third one is strike three, wasn't it? Johnny was down for the count. It's kind of like that first day of school Johnny had. Brand new teacher right out of college. You know, they make you take all those crazy psychology classes if you're going into education because you got to get into everybody's head. So this teacher was using some psychology on the first day. Looked around the class and said, "If anybody in here thinks you're stupid, why don't you just go ahead and stand up now and let's get it over with." So little Johnny stood up in the back. She walked back there right next to him, looked right down at him and said, "Little Johnny, why do you think you're stupid?" "Well, I don't really think I'm stupid, but I hated to see you standing up there all by yourself."
Oh.
Kind of put psychology back in perspective, didn't it? Well, that's little Johnny for you. Moving on to 182, acetylcholine and nicotinic receptors. Acetylcholine, as we know, is a very active neurotransmitter. And I say active, it is an excitatory neurotransmitter in skeletal muscle. Now, if you throw acetylcholine in the cardiac muscle, we don't get a lot out of it. But in skeletal muscle, this is excitatory stuff. So there's receptors throughout the body for acetylcholine. And then they named this one called nicotinic acetylcholine receptors. What do you think the gist of that is? Do you think nicotine can take its place? It'll actually bind to the same receptors that acetylcholine will? That's exactly what happens. So is nicotine addictive? If you take nicotine and it binds to these receptor sites, your body has to produce less acetylcholine. So when you stop nicotine, you have this withdrawal symptoms because the body says, "Thought you were supplying it." Yeah. It's like, well, you make up your mind. What do you want me to do here? So you go through the withdrawal symptoms, the body says, "All right, I'll supply some more, but you're going to suffer for a while till I build production again. Get production back up to normal, then you're all right again." And then this other one is muscarinic acetylcholine receptors. This is not one you want to play around with because you may not get a chance to get it back. Muscarine is an extract from poisonous mushrooms. Yeah, if you got this one taking the place of acetylcholine, you're probably already dead. You don't have to worry about withdrawal symptoms. This stuff will kill you. So muscarinic acetylcholine receptors, there are some there that will attach to certain acetylcholine receptors. And they say these are actually found in the brain. I guess you really ought to know your mushrooms before you start smoking them, huh? Some people may not. So the right-hand side of 183, in comparison of EPSPs and action potentials occur in axons where the voltage-regulated channels are located, whereas EPSPs occur in the dendrites in the cell body. If it ever made it to the axon hillock, it would be an action potential because that is the initiation point of an action potential, which is just past the cell body, okay? That's why it is where it is. The acetylcholine released from the single synaptic vesicle produces tiny depolarizations of postsynaptic membrane. Here's your tiny depolarizations here. We're summing them up. When more vesicles are stimulated to release their acetylcholine, the depolarization is correspondingly greater. EPSPs are therefore graded in magnitude, unlike all or none action potentials, because EPSPs can be graded and have no refractory period because they've never gone past zero. They don't have to refract. They are capable of summation. We're summing up. That is, the depolarization of several different EPSPs can be added together. Action potentials are prevented from summating by their all or none nature and by their refractory period. All or none, they shoot past zero into the positives and they have to refract back to get into a normal polarized state again. Not this one. If these ever get beyond zero, we're already in an action. Okay? And the table 7.4 kind of summarizes what that little paragraph just said. So 7.5. Look at table 7.5 on 185. Here's botulism. You got origin and effects. Pretty neat little table here. There's Carrere. There's tetrodotoxin from pufferfish. Blocks voltage-gated sodium channels. Nerve gas. You wonder how it works. Inhibits acetylcholine esterase. Eventually go in convulsions and die. Spastic paralysis. And there's strychnine, in case you're wondering how your husband's going to die if you live a little of this in his food over several years. This is how you'll find him dead. Prevents inhibitory postsynaptic potentials in spinal cord that inhibit contraction of antagonistic muscles. If it inhibits contraction of antagonistic muscles, then what do you end up with? A lot of flaccid paralysis. Because all antagonism should be opposing. If you got biceps contracting, what's your triceps doing? Relaxing. So if it inhibits the postsynaptic potentials, but that inhibit contraction, then if they're not inhibiting contraction, what are we doing? We're relaxing, right? So what a way to go. Now you know how he's going to suffer. 186, acetylcholine esterase. This is the enzyme that removes acetylcholine. And there they talk about Carrere again on 186. Carrere competes with acetylcholine for attachment to the nicotinic acetylcholine receptors and thus reduces the size of the end plate potentials. This drug was first used in blowgun darts to South American Indians because it produced flaccid paralysis in victims. Clinically, Carrere is used in surgery as a muscle relaxant and electroconvulsive shock therapy to prevent muscle damage. That's what it's used for today. So it is still out there. Acetylcholine in the central nervous system, well, just as short, it's excitatory and skeletal muscle. That's where it's going to be excitatory at. On 188, Alzheimer's disease. Most common neurodegenerative disease and most common cause of senile dementia. Is associated with loss of cholinergic neurons that terminate in hippocampus and cerebral cortex. Hippocampus, that's loss of memory. That has got to be one of the worst diseases out there today.
Alzheimer's.
Yep, Alzheimer's disease. Of course, most people call it old timers. You really don't have to be that old to get it.
You can get it young.
Yeah, that's how horribly debilitating it is.
I think they said that if you had inflammation of the hippocampus, that you're more likely to have Alzheimer's because it shrinks or something. Hippocampus shrinks.
If your hippocampus is inflamed,
Mhm.
you're less
And
likely.
like if you've had it in your life, you're more likely to have it.
So we need to quit long-term memory, is that what you're saying? Possible causes of Alzheimer's and treatments include the use of cholinesterase inhibitors to augment cholinergic transmission in the brain, the use of antioxidants to limit the oxidative stress produced by free radicals, which contribute to neural damage. And of course, we hear about that stuff even with cancer. Any antioxidants apparently are good for you. They say grapes have antioxidants in them. So, you know what? Vitamin E is a tremendous antioxidant. So, I don't know where it begins and where it ends because we just don't know that much about it. But looking at different neurotransmitters here, and a lot of these are neurotransmitters in some parts of the body, and they may be a hormone in another part of the body. But the first list is monoamines. Monoamines derive from amino acids, that's where the amine comes from. Dopamine, norepinephrine, and epinephrine, they list it, although epinephrine is a hormone, are derived from amino acid tyrosine and placed in a subfamily of monoamines called catecholamines. So a subclass of monoamines, the catecholamines, these are some pretty good neurotransmitters. Dopamine, for instance, is a neurotransmitter. Norepinephrine is a neurotransmitter and a hormone from the adrenal medulla. Technically, we could argue that fact. Epinephrine is the hormone and norepinephrine is the neurotransmitter, although they're listed in both chapters because they work so closely together. They're excitatory to each other. These are primary hormones secreted by the adrenal medulla. The other monoamines are derived from different amino acids and are not classified as catecholamines, such as serotonin from tryptophan. What's the association there? Tryptophan will make you sleepy, won't it? Well, will serotonin make you sleepy? Not necessarily, but it's produced while you're sleeping. There's your connection. So people that get off on their sleep-wake cycles, serotonin levels get off. It makes a difference in their mood, behavior. Plenty of serotonin in the system. I mean, if you take drugs like Zoloft that reduces the uptake of serotonin in the synaptic cleft and it stays out there, these people are a lot more mellow. It's like, don't worry about it. He owes you $1,000. Nah. I don't know if it'd make me that mellow or not, but it chills you. I mean, it relaxes the system. This is good stuff. Let's see what else. That's from the amino acid tryptophan. Histamines derive from another amino acid, histidine. Histamine stimulates gastric acid secretion, vasodilation, constriction of bronchioles in the lungs, and other functions, inflammation, and allergies. As a monoamine neurotransmitter in the brain, histamine promotes wakeful alertness. This is why some antihistamines cause drowsiness. That makes sense, doesn't it? Histamine, wakeful alertness. If you're blocking that, you're drowsy. It doesn't take much to make me drowsy. The stimulatory effect of these monoamines, like those of acetylcholine, must be quickly inhibited so to maintain proper neural control. The action of monoamine neurotransmitters at the synapse is stopped by reuptake of the neurotransmitter molecules from the synaptic cleft, or degradation. We can break them down by using some form of enzyme. Destruction. So those are some different classes. I think we'll talk more about probably serotonin here, on the next page. We're seeing serotonin as a neurotransmitter here. Derived from L-tryptophan. Variations of this amount of amino acid in the diet, tryptophan-rich foods, milk, turkey, milk products, can affect the amount of serotonin produced by neurons. Physiological functions attributed to serotonin include a role in the regulation of mood, behavior, appetite, and cerebral circulation. Now, cerebral circulation could be pretty important, couldn't it? So, would you say getting normal amounts of sleep could play a role in your conscious thinking when you're awake? It would make direct influences upon decision making throughout the day, wouldn't it? Why, then maybe that explains why people that gets lack of sleep or lacking their sleep may make more poor decisions. We need serotonin. Now, of course, they say for years that a child needs 8 to 10 hours of sleep. Adults can get by with 6 or 7 hours of sleep. Now they're showing adults need that same sleep. And I can sure tell it when I don't get it. My son comes in from college, I don't know what kind of night shift he's working on. His study shift. He comes in and wants to visit from midnight to 3, when I need to be asleep. And when I'm up and going, I don't see hiding or hair. He's asleep. He just runs his, I guess, whenever he can study is when he studies, and he sleeps when he can sleep, and he's found a niche for that. But that's what I'm going to think anyway. Who knows? But the serotonin plays a huge role in mood, behavior. If you don't get enough sleep, you tend to be cranky, don't you? At the end of the day, when you're tired, you think your serotonin levels are running out. I mean, that's when you're snappy and cranky, and I can see it in my little kids. They come home, well, this time you go to bed. You've already smarted off 3 times in the last 30 seconds. So it's either go to bed or you're going to get 14 whippings tonight. So, yeah, serotonin levels are gone. But the appetite thing, I've seen people take Zoloft, which keeps serotonin out in the cleft, and actually lose weight. And then other people, it mellows them out so much they just eat all the time. So it affects people differently in that way. Because LSD mimics the structure and likely the function of serotonin. Now this is not telling you if you're getting a little cranky to go get you some LSD instead of sleep. This is not what this is telling you. That is not a good decision, okay? And that would be a poor decision on your part. Serotonin, scientists have long suspected that serotonin should influence mood and emotion. Thus, this suspicion is confirmed by the actions of the antidepressant drugs Prozac, which is very hard to get off of. It's somewhat addictive. Paxil, Zoloft, and Lubbox. Now, I know Zoloft is advertised as one that they can wean themselves off, and it should not be addictive because it's typically prescribed in temporary situations. Where I think Prozac is prescribed, I think you better take this the rest of your life. We're just going to try to keep you chilled out. Because they may be borderline postal. These all act as serotonin-specific reuptake inhibitors. In other words, we're not going to take it up. We're going to leave it out there. Use what we have, and hopefully your sleep-wake cycle will build some more where we can gradually get off of that. By blocking the reuptake of serotonin in presynaptic endings and thereby increasing the effectiveness of serotonin transmission at synapses, these drugs have proven effective in treatment of depression. Lack of serotonin is basically a cause of depression. Serotonin's diverse functions are related to the fact that there are many different subtypes of serotonin receptors, over a dozen are currently known. Thus, while Prozac may be given to relieve depression, another drug that promotes serotonin action is sometimes given to reduce the appetite of obese patients. So, there again, playing on the appetite thing. Maybe that's gonna be one of the newer weight loss programs. Now, some people, when they get depressed, they eat all the time. Some people, when they get depressed, they just quit eating. So again, that affects people so differently. Dopamine as a neurotransmitter. What under-the-counter drug do you think mimics dopamine? Not all at once.
Under the counter, what does that mean?
Illegal.
Okay.
Oh.
Under the counter.
Cocaine.
Cocaine. Yeah, sorry, medical terminology there.
Don't get fancy now.
I watch these commercials all the time, and they of course, they talk real fast, and they say, this is the only OTC drug that, I thought, what the Sam Hill? Finally, over the counter is what they're saying with OTC, so I need UTC drugs, under the counter. That's your illegal drugs, okay? So we make up our own terms as we go. Now that we're on the same page, 191. Dopamine as a neurotransmitter called dopaminergic neurons. The cell bodies of dopaminergic neurons are highly concentrated in the midbrain. This axon projects to two different parts of the brain and divided into two systems, the nigrostriatal dopamine system and the mesolimbic dopamine system. Now, they think the nigrostriatal dopamine system is the main area of effect in Parkinson's. Parkinson's disease, in that next paragraph, is caused by the degeneration of the dopaminergic neurons in the substantia nigra. And the substantia nigra, which puts it in this system right here. Second most common neurodegenerative disease after Alzheimer's, and associated with such symptoms as muscle tremors, rigidity, difficulty in initiating movements and speech, and other severe motor problems. Patients are often treated with L-DOPA and MAO inhibitors in an attempt to increase dopaminergic transmission. Here's my question. I would love to see a study on people that have used, in some cases even abused, cocaine, and the long-term effect on them getting Parkinson's. If it's degeneration of dopaminergic neurons and cocaine mimics dopamine, will too much cocaine not burn up those receptors and cause this problem? That's just a theory. I've never seen a study on it. There's got to be somebody studying that. I mean, they did the study on football players and traumatic head injuries. Why not the drug addicts on cocaine? Or even substitutes of cocaine
Not
out
enough
there.
drug addicts are going.
It's not illegal to play football, so it's easier to study them.
Good point.
They're more likely to
Yeah.
volunteer for a study.
Well, I mean, we should have enough drug addicts that have been caught in prison to run a study. And that's fair game. We can run studies on them all day long. Of course, they have more rights than we do and probably get fed more than we do and still don't pay taxes.
And they don't have to pay for TV.
They get cable for free.
They don't have to pay.
Probably Dish
We
Network.
pay for their
Yeah,
TV.
we pay for all their stuff, so. Mesolimbic dopamine system. Here, this is a unique deal. Dopamine released by these neurons may be involved in behavior and reward. For example, several studies involving human twins separated at birth and reared in different environments, and other studies involved in use of rats. That's close to twins, right? Rats, twins. Implicated that the gene that codes for one subtype of dopamine receptor in alcoholism. So what that's saying, we're not going to have time to finish this one today, I'm telling you right now. They're saying that you're genetically capable of alcoholism. It's a gene. Agree or disagree?
I disagree.
See, I knew we wouldn't get over this one very fast. There's just something to study on between now and Wednesday, because we're going to discuss alcoholism being genetic or not. Okay? And there's quite a bit more in this section of the separation of twins at birth, because we've got to throw in society in that process too. So, societal influence. I believe we're done on the filming.